So now we are going to do different processes and dimensionless numbers in this lecture. So let's start with buoyancy and convection, and we will also do Rayleigh number here. So what exactly is buoyancy and how does it create convection? So you see two different images here. One is of the convection due to distributed source, and other one is convection from a single source or a concentrated source. So we all know that concentration develops when there is a density difference, right? And that density difference might be coming because of temperature difference or concentration difference or difference in moisture conditions, etc. Right? So in these cases, as you see, this one, the convection from a distributed source. In here, this is convection from an isolated source. Right, so both are example of convection. So what is happening here? So the fluid that you see here in both the cases, so this white fluid, let's say the hot gas that is here, it may have density rho 1 and the ambient may have density rho 2. So rho 1 is smaller than rho 2. So that's why there is this delta rho which is creating a buoyancy force in this hot fluid. Okay, so this hot fluid that you see here, this creates buoyancy force in the hot fluid if rho 1 is smaller than rho 2, right? And that is why it tries to rise upward. Same case is happening in the previous case. Here, this the convection that you see that is rising up here. This is because the ground is getting warmed up, and that is slowly warming up the air that is in touch with the ground. And when the air gets warmed up or heated up, the density of that lower layer air becomes smaller than the density of the surrounding air, or density above it. So that creates the density difference, and that density difference brings buoyancy force in the fluid or air that is at the lower layer, and that lets the warmed up fluid or heated air to rise up, right? And that is how your convection is created. So to understand this in more detail, let's take an example here. So consider that we have a container which is filled with water, right? And then we start heating it up. Okay, so when we start heating it up, what happens is it this lower part of the water becomes hotter than the upper layer. Okay, so now becomes because it becomes hotter, it transfers heat into the upper layer of the fluid. So heat gets transferred upward, right? So the moment you start heating up, the heat transfer starts happening, right? So in the beginning, when the temperature difference of the bottom fluid and the upper fluid is not much, the heat transfer happens only through conduction, right? Heat conduction. So it early time when delta T, that is the temperature difference between the bottom layer fluid and upper layer fluid is not significant, then transfer occurs only through conduction. Okay, so why it happens only through conduction? Because buoyancy force is still small to overcome the viscous force, right? So what happens is you start heating it up, temperature rises, so it creates buoyancy force, but that buoyancy force in the beginning is still very small, that the viscous force in the fluid is not overcome by the buoyancy force, right? And that is why there is a resistance in the fluid for fluid motion, and that resistance is because of viscosity, and that happens in the beginning, right? But now you continuously heat it up, the delta T continuously increases because you're constantly supplying heat. So when you continue, the delta T becomes greater than, if you continue heating, delta T becomes significant such that the buoyancy force becomes greater than the viscous force in the fluid, right? So this is at later time. Okay, so at late times when you continue heating it up, buoyancy force increases, and now there will be a point when buoyancy force in the fluid, in the bottom layer fluid, will become greater than the resistance offered by the viscosity. And when that buoyancy force becomes greater than the viscous force, convection begins. So what is convection? That is basically the motion of fluid parcels, right? So in that case, this is when convection begins. You know, what is the difference between conduction and convection? In conduction, only heat transfer occurs. Okay, so there is heat transfer through molecular process, but when it starts convection, also your fluid parcels are moving. So the fluid that might have got heated up, let's say if this fluid parcel which got heated up now, this fluid parcel itself will move. Okay, so that happens in case of convection, not in case of conduction. Okay, so in case of convection, fluid parcels also move, and therefore heat transfer increases. Okay, so as convection begins, you get more and more heat transfer. compared to conduction. Okay, and what exactly is happening in case of convection? You are having higher buoyancy force compared to the viscous force. So now if you want to quantify this effect, like beyond which conduction will be there and beyond what point you will have convection. So for that, we need to achieve a certain temperature difference. Only beyond that you will achieve convection. So this particular process is actually defined by a number called Rayleigh number, which gives you the ratio of buoyancy force to viscous force. Okay, and for it has different forms, but the most general form of buoyancy force is defined as alpha G delta T H cube over nu K. Okay, where alpha is the thermal expansion coefficient, G is the gravity, delta T is the temperature difference. Okay, and H is the length scale, mu is the kinematic viscosity, and K is thermal diffusivity. Okay, so these are different uh, parameters we have, where H, the length scale, is the vertical length scale. So if you think about this particular water body, we are talking about this length scale. This will be your H. Okay, and then we have delta T. Delta T is the temperature difference between the bottom fluid and the upper fluid. All right, so what you see in this particular equation is this alpha G, delta T, and H cube. So delta T basically brings the buoyancy term, right? And that is that creates the buoyancy force for convection to happen. In contrast, what you see in denominator is the viscosity. You can see new kinematic viscosity. So if you have more viscosity, that means you have more viscous force. It will require higher delta T to start convection, right? So what exactly we know here is for so there is a critical Rayleigh number. We'll come back to this particular table once we have discussed the critical Rayleigh number. So, RA critical is about 1700. So if RA is smaller than RA critical, you have viscous force greater than buoyancy force, and heat transfer is only through conduction. Okay, and if Ra is greater than Rec, in that case, now convection dominates. Okay, so your conduction and convection depends on the critical Rayleigh number. If your critical Rayleigh or the Rayleigh number of the flow or heating is smaller than 1700, then there will be no convection. Okay, it will happen only through conduction because there is higher viscous force. If Rayleigh number is greater than the critical Rayleigh number, then you will get convection. And in conduction, heat transfer will only happen through convection. Okay, now coming back to this table where you can see the properties of both water and air, all these three properties: thermal expansion coefficient, kinematic viscosity, and thermal diffusion. Okay, so these are the usual values that we use, and these values will be given in case we have to solve a problem related to this particular case. Okay, so that is the buoyancy force and convection. Now let's go to another process which is equally important, and that is transport and freight. So we have been looking at this second example quite often, where we talked about convection with regards to the second example. In this case, we also have, so once convection begins, that is one part, but now what we are more interested in is the transport and fate of these contaminants. So these contaminants are rising up because of buoyancy force, but what happens next, right? So as you can see, this fluid that you have here has risen up and it's actually flowing sideward, right? It is getting mixed into the atmosphere, it is transporting from one place to the other. Likewise, in this example that you see, there is this hot gas coming out due to the stubble burning, and it will rise up and then it will again go mix with the atmospheric air, and it will maybe transport to nearby cities or towns, and it will create air pollution. And that is exactly what's happening currently in major cities like New Delhi during winter time. So here there are two particular things. When pollution happens, it happens because of transport and eventual fate of these contaminants. So what exactly transport means is the physical process, right? So transport belongs to the physics of flow, whereas fate belongs to the biochemistry of contaminants. So basically, how does it mix with air, or how does it affect our body if we inhale it, etc. So that is the biochemistry part, and we are not really concerned about biochemistry. We are more concerned about the physics of flow, or transport of contaminants from one place to the other. So this transport actually accounts for both, accounts for flow plus mixing. So when fluid goes from, or contaminants flow from one point to another, it flows at the same time it mixes with the surrounding fluid. So in this case, this hot gas is mixing with the air, right? So we are interested both in how it is transporting and how it is mixing. So the first part, transporting or advection, is more related to just the plain movement of the fluid from one point to the other because of the pressure difference, whereas the mixing part comes because of either temperature difference or because of contaminant concentration difference. Okay, so let's first study mixing, and flow part is something that will come into picture eventually when we discuss all these problems in more detail. So to understand mixing, let's take this example. Okay, so we have a glass of water and we put a sugar cube into water. Okay, and what happens is, as you can see in this particular case, let's call it case 1, case 2, and case 3. So in case 1, it starts diffusing, mixing with water slowly, right? You just put the sugar cube. After some time, you will see some part of sugar cube has got dissolved and water has got mixed little bit. At time t2, so this is time t1, this is t2, which is greater than t1. Larger part of sugar cube will have got dissolved and more water will have got mixed with sugar cube. And now at T3, which is maybe much later than T1 and T2, so let's call it that is T3, which is greater than T2 and greater than T1. So in this case, sugar cube has completely dissolved, right? And when it has completely dissolved, water at each point in the glass will have some concentration of sugar, or it may have equally distributed sugar. So why exactly it is happening? That happens because of a process called molecular diffusion. Okay, so let's define molecular diffusion first. This is transport of solute molecules from the higher concentration region to lower concentration region due to chemical potential. Okay, so what exactly happening here is whenever you put some material which is soluble in the fluid, there it creates a chemical potential which actually transports or which allows the solute particles to move from higher concentration to lower concentration, okay, which we have seen in this example. And how exactly it happens is we can actually quantify it using this formula. So we can define Fm, which is proportional to delta C by delta X, okay, where Fm is the mass flux of solute. So how much solute transports from one point to another depends on the concentration difference. Higher the concentration difference, the higher will be mass flux, right? So delta C is the concentration difference and delta X is the length scale involved. Okay, so this basically is directly proportional concentration difference and inversely proportional to length scale. So if you have the same concentration difference over a long uh, length scale of interest, then mass flux will be less. Okay, and this mass flux of solute that you have here is generally given in kilogram per unit area per unit time. Okay, so this one has a dimension of kilogram meter square second. Okay, so this is the mass flux of solute. Now if you want to get rid of this sign of proportionality, it is defined as minus dm delta c by delta x, or it can also be written as dc by dx depending on uh, what is your length scale. So this one is particularly valid when delta x is very small, when delta x tends to 0. Okay, in that case we can assume Fm is equal to minus dm dc by dx. So what exactly this dm is? Dm is known as the molecular diffusion coefficient. Okay, so molecular diffusion coefficient, and it depends on solute and particular fluid. So for instance, dm of salt in water roughly equal to 10 to the power minus 5 centimeter square per second, which is almost equal to 10 to the power minus 9 meter square per second. Okay, so this is the molecular diffusion coefficient of salt in water. So as you can already see, this is material dependent, and now the in water, if you want to add sugar, it will have a different dm value. Okay, at the same time, uh, dm is actually a function of temperature. So if you increase the temperature, you get much faster mixing, right? If you go back to this example, when you have sugar, if you add the same sugar in hot water, it mixes much faster. That is because your dm value actually increases with temperature, so mixing is higher. And another thing that you will note here is the negative sign, right? So in this case, we have this negative sign in this equation. That is because it goes from higher concentration to lower concentration. Okay, because dc by dx by default is a negative value, and that multiplies with negative sign, so that gives fm as positive value. Okay, so this equation that we have derived, fm equal to minus dm dc by dx, is known as Fick's first law. Okay, this is known as Fick's first law, and this is specifically valid for steady state condition, where we are only trying to uh, find how much mass flux will occur for a given condition at a given time. But now, if this condition is changing continuously, for instance, in this case, uh, we might not be able to use the same equation that we have derived there. So consider this example where you have two different blocks. One has C equal to C naught, the red fluid that has concentration of C naught, and the blue fluid has a concentration of 0. And we are assuming that there is a barrier in between, right, at time t equal to 0. So let's assume this is time t equal to 0, here time equal to time t1, which is obviously greater than 0, and here t equal to t2, which is greater than T1. So at time t equal to 0, both the fluids are separate, but we remove the barrier and then we see some mixing at time T1. But now after time T2, we see even larger mixing zone, right? So you can call this one as mixing zone, and this mixing zone is smaller in case of time t1, and it is greater in case of time t2, right? And now if you want to see the distribution of concentration in space and time together, in that case we are not able to use this equation that we derived before. In this case, we need to solve this as a two-dimensional problem. So dc by dt is defined as dm d square c by dx square. Okay, so this is known as Fick's second law. Okay, that gives you distribution of concentration both in space and time. Okay, so when you have to solve for mixing in both space and time, in that case you need to use this particular equation, that is Fick's second law. Okay, so this is molecular diffusion, which is happening because of chemical potential when molecules move from one point to another just because of concentration difference. But now let's assume there is flow as well in the field. So this mixing rate of mixing gets enhanced, right? So there is a thing called shear dispersion, which we are going to discuss now. So let's assume that there is a boundary layer. So this is a flat plate, okay, and there is this fluid coming from this side. So what do we know about the boundary layer is there is this velocity profile. So velocity is zero at the bottom at the solid surface. So this is solid surface, and this is, if we assume that this is x-axis, this is y-axis, so what you have here is u of y. So velocity is increasing with vertical axis, right, with y-axis. So in this case, now if you have any contaminant, let's say you put your sugar cube somewhere here, okay, or instead of sugar cube, let's consider that there are so many the contaminants placed in the fluid. What will happen is it will not just mix due to molecular diffusion, but it will get affected by the this velocity gradient in the flow. Okay, so to understand that, let's look at this example that is shown here. So this is the velocity profile, the this particular one, that is shear flow. And what exactly does shear flow mean? When there is velocity gradient in vertical direction, or in transverse direction, right? So you have different velocity as you go uh, normal to the flow. So that is the shear flow. And in this case, we assume that this particular place here has some concentration, right? Some solid particles initially. Now, because there is this velocity gradient, this whole plug of pollutant will move with the velocity. Now, because the upper layer has higher velocity than the bottom layer, this part actually will move faster and this part will move slower, right? So upper layer is moving faster, lower layer is moving slower because of the velocity gradient, and this is happening because of advection. So your whole fluid from here to here is going because of advection. So that part is advection, where contaminant is moving from one place to another, right? But once it has advected from one place to another, there is this now there is this concentration gradient between the contaminants and ambient fluid, right? So there is this molecular diffusion in transverse direction, and that is how you get higher mixing. So after some time, when it has got advection, and this one now you see is molecular diffusion. So this process of mixing has got enhanced because of this shear force or shear flow, right? And the overall mixing that you see is now this one, right? So the total mixing is enhanced due to advection and diffusion together in a shear flow, right? So that is an enhanced mixing. Now if you look at the same example and you assume that there is this contaminants and we have fluid going in, coming from one side, and there is no shear flow, okay? So in that case, probably you will still see mixing, but this will be only small. So what you see here, this mixing will only be because of molecular diffusion. Okay, so if there is uniform flow, if there is not shear flow, only uniform flow, so the total mixing you will get will be just because of molecular diffusion. Whereas in this case, when you have shear flow, the mixing gets enhanced because of advection in longitudinal direction and diffusion in transverse direction. Okay, so going back to this one, this enhanced mixing is basically longitudinal advection plus transverse diffusion is equal to enhanced mixing in a shear flow. Okay, so this is what happens when you have shear flow. And once again, what is shear flow? There is gradient of velocity. Okay, so now we want to quantify at what condition you have more advection, or mixing is more because of advection or more because of molecular diffusion, because mixing is happening because of both, right? Or both are influencing the enhanced mixing. So we define a number called Peclet number, okay, which gives you the ratio of longitudinal advection over transverse diffusion, which is usually just written as advection over diffusion. Okay, so this is Peclet number, and this is defined as this is a particular formula which I'm just okay. So this is UL over DM. Okay, where U is the advection velocity, or simply the velocity of the flow. And this obviously, now we know that there is velocity variation. So we generally take the characteristic velocity. So for instance, in this case, we can assume this to be U here, which is the free stream velocity. So that is the characteristic velocity. And then L is the length scale, which both velocity and length scale are defined for a particular situation. And dm is the molecular diffusion coefficient, which we have already defined. Okay, so if Peclet number is greater than 1, that means your UL is greater than dm. In this case, advection is greater than diffusion. So your flow is actually dominated by advection, or the whole mixing process is dominated by advection. And if Peclet number is smaller than 1, then your UL is smaller than dm. In that case, advection, or in other words, diffusion dominates, where diffusion is greater than advection. Okay, so this is the Peclet number which is used to quantify the effects of diffusion over advection, or advection over diffusion for a particular condition. And this process of enhanced mixing is known as the shear dispersion, or also known as Taylor dispersion. And this particular kind of problem is solved using advection diffusion equation. and I'll call it simplified version. So this actually is given as dc by dt plus u dc by dx is equal to d square. So here there should be dm dy square. Okay, so this is the advection diffusion equation where this is the unsteady or accumulation term. The second term signifies the longitudinal advection, and the third term is the transverse diffusion. Okay, so we see three different terms here. First is the unsteady term, which basically tells you how concentration is changing in time. Second term is the longitudinal advection term. So basically, as we have seen, velocity is going in one direction. So whole block of fluid is actually moving from one point to another. That is coming because of this longitudinal advection term. And then the third one is transverse diffusion term. So this is basically the molecular diffusion term. And that's why we have the d square c by dy square. And there is this dm term as well. Okay, so this gives you the overall mixing pattern for a system with advection and diffusion. But please note that this is a simplified version. So this is particularly written for this case when we have dominant velocity in only one direction, and then mixing in another direction. But usually the flow profiles are generally much more complex. In that case, we will have to use a full-fledged advection diffusion equation with all other terms, and that is something we are going to see in coming lectures.